1 2 1 2 3 1 2 3 4.
Ủa?
Một hai ba bốn, 1 2 3 4 5, 1 2 3 4 5 6 7 8 9 10, 1 2. Được không? Do kính anh, phòng kính không mà không vang sao được. Giờ mua xốp dán hết phòng hết vang. Nghe nó bị 2 tiếng không? 3 tiếng không?
Hôm nay em lý mặt có 1 tiếng thôi. Có cái là em đứng gần thì cái nó ổn định hơn. Còn đi xa thì vang.
Đứng gần chắc. Nếu mà đứng tới đây là hết cỡ này.
Bây giờ cái máy thì nó chút xíu rồi.
Đeo là nó bị kiểu bị trùng. Không không, tại vì như kiểu là muốn đi tới đây thì sao?
Thì nó bây giờ sao, bây giờ không có chịu thôi. Bây giờ cỡ hơn 5 tệ.
Hỏi thử với nó được chịu không?
Thì cứ rồi. Rồi giảm sát cái này chứ.
Để đâu ra bật đèn chút. Bật đèn chút để đâu ra. Đó nè, đó là như kìa. Ở dưới kia. Cái này đẹp á, cái này đẹp á.
Sao ạ? Nặng nha.
Cái góc đây phải để này không biết có bị giờ cái gì, còn phải đến thử để làm cái gì. Năm nó làm ăn lên kia rồi. Mình đi nốt mà đi chơi mà ngồi đi. Nhiều con. Em đi không có hội có mình bán này còn biết che
con cái tôm đây cái ba này em công ty với Hiền đúng không? Anh Tư Hiền Quân này.
Cương
Nghĩ hả? Nghĩ xong đó hả? Lâu quá không gặp hả? Anh nghĩ bên đó mà qua
Nó có phòng tập tắm chưa? Đây là có tập cái này là không cái có đây có phòng tắm sẽ bay và chúng ta có tiền kho thì tiền
Oh, it's over to add the files that we needed.
yeah, so you have to get some
Yeah, exactly. Yeah.
Test nghe được không ta?
Excuse me. I was trying to
Cái dây này á, nó bị sẽ rất là dễ dẫm vào luôn á. Mọi người nghe. Ok, như vậy là bây giờ cái này bỏ ra đúng không? Nhưng mà lúc mà nói thử là mọi em nghe được đúng không?
Cái này hả? Nhưng mà nếu mà cài là mất 1 phút nha.
Mọi người ở bên Ashwa, welcome mọi người. Mọi người ăn sáng chưa? Bánh cà trà cà phê ở ngoài nhá. Free mang vào nhá.
Nếu mà cài cái này chỉ cài đây cũng được.
Ok. Mọi người ra đi tranh thủ ăn sáng thì đỡ đói. Mọi người nghe được không? Thử không?
Nghe ok rồi.
Ok đúng không?
Là lát hồi chị đứng như thế nào? Đứng ở đây là đứng ở đó.
Chắc 5 phút thôi à? Yeah, đứng đây 5 phút chị nói xong rồi đến anh này luôn. À,
50 phút.
À 50 phút nữa mà đúng không? 10 giờ.
Dạ.
10 giờ bắt đầu có kịp không?
10 giờ bắt đầu. Ok, chắc kịp á.
Ok, thế thì
Bây giờ tạm thời cứ vậy đi.
Ok. Thì cho anh kia thì ok. Yeah. Hello, welcome mọi người. Nào. Cái này mình chắc bỏ gọn vào một góc được không ta? Đây là chắc cứ bỏ tạm ra nha.
Like I'm going one step further and saying that like because like once I execute, I want to be like I kind of
Mọi người ơi, chắc là mình sẽ bắt đầu sớm trong vòng vài phút nữa để cho mọi người không phải chờ đợi lâu á. Và xin đề nghị các bạn là trong lúc mà có diễn ra buổi workshop thì các bạn vui lòng tắt điện thoại giúp được không? Tất cả để trong chế độ im lặng giúp mình nha. Tại vì không gian này nó hơi nhỏ và cái mic này nó cũng đủ lớn á, cho nên là hy vọng là các bạn có thể nghe được rõ hơn và tránh tiếng ồn. Và chương trình của bọn mình cũng sẽ có livestream ở trên website, cho nên là hy vọng rằng là sau cái buổi này cũng sẽ có các cái tư liệu online để chia sẻ lại trên website để các bạn có thể xem lại. Ok. So hi everyone, thank you very much for joining our first workshop with Web3 Vietnam today. We will start soon, so please be settled and please kindly take off, turn off your phone or put it in the silent mode, please. Thank you so much. Okay, so I think that everyone is settled. So let's start. Hi everyone, welcome to Web3 Vietnam. Thank you all for joining us today for our first workshop. And first of all, we would like to introduce our mentor, our speaker today, Barry Whitehat from Ethereum Foundation. And also today, we also have other supporter and also other sponsor for this. Actually, F&B sponsor from AWS, from Dons and the AWS team. And even though he got some injured, but he comes today to join the workshop with us. He really loved to join this GK knowledge proof workshop. And also have other support team, Mustbit team, also from QuickCom team, and also all of you guys from many familiar faces that I know here, Kyber, and many other teams, Cypher, and many other community members also. Thank you very much for joining the workshop. So first of all, I would like to let you know about the series of the workshop that Web3 Vietnam will do. So the purpose, why we do this, because we see that we can, supporting and also connecting the global team and also the local team, and also focus on the technology and also the dev community. So we believe that with that we can have all of us leverage our own knowledge, and also together we can build the better projects. And thanks to many other experts and also mentor like Barry Whitehat today. We hope that you also enjoy the workshop and we can learn more new things. So I don't take the stage anymore. Please welcome Barry Whitehat.
What is the schedule for today?
Okay, sorry. So the schedule today is very simple. First today we just have Barry to share the basic knowledge about ZK knowledge and also about project on Ethereum ecosystem. And also after that, we also love to hear from you guys from the local community, what you are doing, what you're building, and also what is your expectations. So we also know that what we can do better for the other workshop. And also for tomorrow, Barry Whitehat also have more technical workshop, focus more on the technical part, and also we can have some challenge or building something together, and you might use a laptop to do some fun thing with Barry Whitehat. Okay. I will take the micro at the free one later in 15 minutes.
Okay.
It's coming.
Okay. Okay, do I have a thing for the slides? Okay, anyway, so today I'm going to talk about a couple of things. First of all, we're going to start with the introduction to some things that you can build with privacy. This is going to be a sort of basic introduction to like what ZKPs are and like what they do, but we're not going to talk about like how they work. So we're going to do that, and then after that we're going to talk about like some of the different applications that have been built already, and we're going to see like some of those things. And then after that we're going to talk about like a bunch of scaling, how ZK rollups and optimistic rollups work, and we're going to discuss about like how you can make like secure bridges and things like that, and how you can make like more scalable transactions on layer 2. So that's kind of my plan for today. The first part is kind of more prepared. I have slides to discuss. Quinn, is there something for the slides?
Yes.
Oh, thank you. So the first part is more prepared, and the second part is a little bit more open. My plan is to like go through that stuff, and then like I'd be happy to have some interaction, because it's going to be mostly on the whiteboard, so we can talk about it, and like I'm happy to get questions and deeper discussion about things. So like on the second part we can go like whatever direction is interesting for you all. Like my idea was to talk about like layer 2 stuff, because that seems like a important topic in the community in Vietnam at the moment. So I'll spend some time doing that, and like if you all want to go in another direction, I'm happy to talk about other stuff too. Yeah, so that's kind of roughly the plan. So maybe we'll take a break in the middle, because it's like a long time. It's like 2 hours. So maybe we'll take a break after we go through like the first section, and we can have some coffee and some tea and stuff. But yeah.
Sorry, I know like he had to change the slide, the remote slide will come.
Okay, that's all good. Yeah. Okay, so yeah, so let me talk about like the background knowledge so let's start the privacy part, and let me first talk about like the background knowledge that's required. So like I'm not assuming any background knowledge here. This is like an introductory presentation. So the background knowledge is basically nothing. Just have an idea of like how computers work, and how you can define programs and things like that. But that's the main background knowledge that's required. But like there is a couple of things I'm going to explain right now that are important, and the two things are like hash functions and Merkle trees. So can I get the next slide, please? Yeah. So the first thing to talk about is hash functions. So basically, what a hash function is that like it's kind of this like irreversible thing that you give it some input, you give it like a big input, and it will give you a small output. And it's impossible to take the small output and go back to the big input. So yeah, so that's kind of what's described here in this picture, that you have this like big input on the left-hand side. It enters into our hash function, and on the right-hand side you have this like completely random output. So like that's what a hash function looks like, but like the output has to be much smaller than the input. Like the point of this is that we're able to use it to turn like big amounts of information into small amounts of information. And that's important because like we want to have like very small descriptions of things. So that's what we use hash functions to do. We use hash functions to do this in conjunction with, we use hash functions to build what's called a Merkle tree. So can I have the next slide, please? Yeah, this one. So like a Merkle tree is basically like this thing that you make with hash functions. So a hash function will take in this big input on the bottom, and it'll kind of like combine it together with each hash into a smaller. So you see at the bottom it takes in this big amount of data, L1, and we hash it. And then the size of the result is much smaller. So then we take the output of hash 00 and hash 01, and we hash that together again, and we just continue doing this until all of our data has been compressed from being like really, really big into just a single top hash here, which we call the Merkle root. So the Merkle root is normally like it's really small, and we use the Merkle root to commit to things on chain. And like the reason we want to commit to things in a small way is because we don't have a lot of storage on chain. We want to store only the minimum amount of information we can. The other thing that Merkle trees let you do is to do something called a Merkle proof. That you're able to prove that like some data is inside the Merkle root, and that proof is really, really small too. And basically the way that you do it is you just take a single leaf and you kind of hash it together with its neighbors all the way up the tree, but you only need to know about the neighbors. So yeah, you only need to know about the neighbors. So if you look at the like left-hand side here, if we want to prove membership of L1, all that we need to have is L1, hash 01, and hash 1. That's all that we need to have in order to be able to prove that L1 is part of the tree. So like if this is too difficult to understand, we can just abstract it away. And like we can abstract it away by saying that like it's a, and that's all that you really need to know on like the highest level. So often when we're doing ZKP stuff, it's hard to understand all of the complexity of like these systems. So like what we try and do is try to abstract away the components to kind of black box out the pieces that we don't understand, or black box out the pieces that are like a little bit too much information for us to try and explore right now. And that way we can still like make progress on what we're doing, while also like later being in a good position to learn about like what else we need to do. So that's a big part of like the philosophy of this presentation, is we're black boxing out a whole bunch of different things, and like the idea here is to get a high level view of what's possible, and from there we'll be able to sort of like see what's possible, and then we can make decisions about the specific things that we want to learn, so that we're still able to make things, because like you can make things with ZKPs relatively easily, or like it's possible to make them without understanding all of the math. Like a lot of people think that like, oh, I want to make something with ZKPs, so therefore the first thing I need to do is learn about abstract algebra. But that's not really the case, because like when you want to make something with a smart contract, like you didn't, like when you started to make something on Ethereum, you didn't say, okay, I want to make something on Ethereum. The first thing I need to do is learn how ECDSA signatures work, right? Nobody ever does that. Everybody says, okay, I understand what a signature is. It's like a signature that you write on a letter. It's like only you can make the signature, and everyone else is able to verify the signature. And that's what a signature is. And that's like, and now we've successfully abstracted away this concept, so we don't have to worry about studying ECDSA signatures before we're able to like make our first Ethereum hello world application. So like let's take this approach and let's apply this to like the ZKP problem, where we're going to abstract away the different components that we're going to learn about later, so that we're still able to make like our proof of concept applications, and we're still able to like play and learn and figure things out in a way that like we're making incremental progress, rather than we're like studying a lot and then like a year later we're able to make our first application. So okay, so that's kind of like the plan here in this presentation, and like that's also been my plan like when I've started to learn about these things. I often just try and find the specific piece I want to learn about and try and black box out the other pieces as much as I can. Okay, cool. So can I get the next slide? Oh yeah. So that's what a Merkle proof is, and that's what a hash function is. But the other important piece of like introductory or like background knowledge that I would like to share is like, what is a zero knowledge proof? Because I'm sure you all have heard a lot about zero knowledge proofs being used for like private applications and like scaling. But like the definition of ZKP is pretty simple. It's basically, I want to prove something to someone. Like you can give a proof to someone that someone can check, and like when someone checks the proof, they basically just check everything that you've done, and that's not a zero knowledge proof. That's just a proof. So when we want to do like a zero knowledge proof, it's very simple. It's basically what we want to do is hide the information that we use to prove the statement. So a zero knowledge proof is basically like, I can prove to someone that something is true without revealing why it's true. Okay, so that's what a zero knowledge proof is. So could I get the next slide? Cool. Okay, so yeah. So this is how we're going to talk about zero knowledge proofs. We have this like visual representation. And there's two, oh, I think we went 2 slides forward. Could we go back 1? Oh, yes, this is right. So when we see zero knowledge proofs, there's gonna be 2 views that we think about, right? The first view is the view of the system of the prover, the way that the prover sees the world, the ZKP. Because the prover, in order to make proofs about something being true, the prover needs to know that it's true. And like, they need to know all of the information about how they're proving it's true. So for the user, there's no zero knowledge. Or for the prover, there's no zero knowledge. The prover knows everything about the proof, and they know why it's true. And like, basically they use the zero knowledge proof to turn the like description from like zero, to make a description that's private for the verifier. So, thank you. So, here we go. Okay, so, sorry, try it. Oh, it's off. Huh. Oh yeah. Okay, we got it. So where was I? Right. So the prover knows everything about the system, because in order to make the proof, they need to know why it's true. And they use the zero knowledge proof to hide it from the verifier. And like, when we talk about this, it's going to look like this. When we're talking from the prover's point of view, see that like, we have a certain set of public inputs, we have a certain set of private inputs, we have the check that's being performed, and then we have the output. And this is like the most basic circuit that I could come up with, which basically says that, okay, I take a public input and a private input, and then I multiply those 2 together, and I say that it has to equal C, and then I return C. So like, one like use case of this circuit could be like, I want to prove to someone that I'm able to perform a multiplication. I'm able to multiply a number A by B, and that it equals C. And like, I don't want to reveal what B is. So like, that's one of the applications. That's like a very simple application. I don't think that like this circuit would be very useful. It's more like an example. So that's the circuit. That's our basic circuit. And like, let's see what it looks like for the verifier. So, oops. A little lag. Okay. So for the verifier, we see that. Okay. Yeah. So this is our prover, and this is what our verifier sees. Okay. I wanted to be able to cycle through so you can see the diff, but like, basically the difference is that we've hidden this variable B. Oh, this one is supposed to be hidden too. This B and this B is supposed to be hidden, because like, inside the ZKP, we sort of hide the variable B. So anyway, so far I've just talked about like, this is what a ZKP does, and I've given like a simple example of that. That's like, it's not very useful, this circuit, but it is going to be useful later to have this like abstraction or this way to discuss circuits. Okay, so let's go to the next one.
In the verifier views, we can still see the input, right?
Yeah, so you see, oh yeah, okay, that's a good thing to mention. So, okay, so the prover sees everything. The verifier sees A and C, but they don't see B. Yeah, there should be a box here. I'm sorry, I messed up the slides. There should be a cover for the B, but the rest of them should be covered. The other thing to notice is that like the verifier sees A and it sees C, but they also see the check that's being performed. They see that it's like A multiplied by something equals C, and that's important to remember, because like if you have like a 0-0 knowledge proof where like you don't know the check that's being performed, that would be like kind of meaningless, right? Because like you need to know what the person is proving. Because if you didn't know what they were proving, then it would just be like it wouldn't be very valuable. So the ZKP also reveals the checks that are being performed. It just hides some of the input values to those checks.
What's the analogy of like prover and user or a verifier in some application?
Sure. Okay. So let me see. So let's take the example of a mixer. So a mixer is where you like deposit some money to a smart contract and you make a ZKP to withdraw that money to a new address. And in that case, the prover is a user who is deposited. Yeah, user deposited like some token inside, and when they're withdrawing, they need to make a proof that like this is my money. And the verifier is the smart contract. Yeah, the smart contract will verify this proof and says, oh, look, you deposited money, you made a ZKP, now you're able to withdraw it. So that's an example, and that's the example we're going to talk about next. We're going to take this example of Zcash. Yeah, so Zcash is like a mixer, but so Zcash is like a mixer, and basically it's a way to So Zcash is like a mixer, and basically it's a way to like you can send private transactions to people, and basically so Zcash needs to verify that like transactions are correct, and it does this using zero knowledge proofs. It also needs to prevent that to make sure that like when I say transactions are correct, we need to make sure that the owner of that coin is consenting to this transaction. And basically we do that with like a signature check, and we also have to, I'll talk about that in a minute. So like, first of all, they prove ownership of the funds, and secondly, they prove that they do something to prevent them like double spending a coin. Like double spending is a big problem on like in cryptocurrency in general, and all different cryptocurrencies have different approaches to prevent it. And with Zcash, the way that they prevent it is using a nullifier. So basically, I'll talk about a nullifier in a second. Let me go to let's bring up our first abstraction. Okay, that's too far. Just go back one. Okay. So this is what our prover sees, right? Our prover sees everything. They know all of the states of the system. They're using the ZKP to hide some of the information. So I'm a little bit okay. So let's look at what we have here. So the first thing we have is a Merkle root. So let's remember what a Merkle root is. So a Merkle root is basically a way to like commit to data. So in this case, our Merkle root is like all of the coins that have been deposited. So we have our Merkle root, and this is like a public input. And what's our public output is our nullifier. So basically what we have here is we have something that sort of like says that like this user has spent this coin, and then the nullifier prevents them from spending it again. So let's look a little bit deeper about how exactly we achieve this. So we have our Merkle root, and we have our private inputs. So let's look at our private inputs. So our first private input is our Merkle proof, and that's basically proving something is part of the Merkle root. It's proof of membership. We have our public key, and we have our private key. We have our public key and private key to verify the consent of the user. The user is consenting to make this transaction. So we have the oh no. Okay. So the public key and private key is here to consent to the transaction. That users need to be like, yep, I want to send this money to here. And the final thing that we have as a private input is our nullifier. And our nullifier is to prevent the double spend. So let's see how these are actually consumed. So let's look at our checks, the checks that we perform inside our ZKP. So the first check that we perform is our membership check, right? We want to say that, well, you can only spend coins that are valid. You can only spend coins that are inside our Merkle root. So how do we do that? Well, we do a membership proof that basically takes the public key, the Merkle root, and the Merkle proof, and it proves that like the public key is inside the Merkle root. Yeah, that's our first thing that we're doing. The user is coming along and saying that I want to send this transaction. Here's proof that like I want to spend this coin. Here's proof that like this coin is valid. This coin exists. So that's what our oops. So that's what our first check does. Our first check is just about like this is a valid leaf. This is a valid coin. This is valid money. And then the second thing that we need to do is we need to check consent. Oops. Okay, it's working better. Okay, and the second thing we need to do is we need to check consent. So how can we check the consent of the user? Well, we use a signature scheme normally. So I made this like very, very hacky signature scheme here, which is basically just a hash function. And the way that the signature scheme works is, the way that the signature scheme works is that like you have a hash function, you have the private key, and you hash it with a nullifier, you calculate the public key. And like the idea here is that like the private key and the nullifier is only known by the user. So if someone is able to make this hash function that from one can calculate the other, then only they know that, so only they can make that proof. Therefore, it's a signature that like only one person can create, and so it's a good signature scheme. Okay. So this is the first slide. Yeah. So this is where we want to be. So that's what our hash function is doing here. So it's basically taking the private key and the nullifier, and it's calculating the public key. And then the final thing that we're doing is that like, okay, so what's this concept of the nullifier? So the nullifier is this thing that can only be spent once, right? Oh, so the nullifier is this thing that's like deterministically calculated from the private key. So when a user makes a coin, they make a new private key and a new nullifier. And every time they spend a coin, they say, okay, here's the nullifier of the previous coin. And the idea of the nullifier is that it prevents people from double spending the same coin. So like when we have privacy, we have to make sure that people aren't able to like infinitely spend the same money. So we use a nullifier to prevent this, because the nullifier is this like it's like, oh damn it, it's my fault. I keep pressing the wrong button here. I keep trying and point the laser. So okay, so that's what the nullifier is. Oops. Okay, so let me not use the laser. I think that will help. Okay. Yeah, so that's what the nullifier is. So the nullifier is basically like prevents you from spending the coin more than once. The nullifier is so like let's talk about like what the verifier sees. Let's talk about what the verifier sees. Okay, here's what the verifier sees. So the verifier sees a lot less than what the prover sees. So the verifier basically sees that there's a Merkle root, that like the verifier also has a list of valid coins. And the verifier says that I'm only going to let people spend coins that are valid. So in the smart contract or in the Zcash protocol, the verifier will remember this Merkle root, and they'll only allow proofs of the Merkle root. They'll only allow proofs that have this Merkle root as the public input. So yeah, that's how the verifier limits the set of valid coins. The other thing that they have the Merkle root, and then so what do they actually do? They verify the proof of membership, but they don't know which coin it is. and they also verify like the signature, but they keep they reveal the nullifier, right? Because we want to see what the nullifier is, because we need to use it to prevent double spends. So like the other thing the verifier will do is they'll store the nullifier in the smart contract, and they'll basically say you can only spend one nullifier once. If you spend a nullifier, if two proofs have the same nullifier, the second proof is invalid, right? Because that means someone's trying to like double spend the same money.
How can the verifier execute the membership without the Merkle proof and others keys?
So the question is, how can, just for people on the live stream, so the question is, how can the verifier verify the proof without the data, without the proof of membership, without the stuff that we saw on slide 1? And okay, so like the answer to that is kind of like outside the scope of this presentation. So basically what I would say is that like we use the zero knowledge proofs to do that, and like the way that zero knowledge proofs do that, let me try and give an intuition for that. Okay, so like one intuition that I have about this is saying that like if you want to be 100% sure that something is correct, you have to try really, really hard. You have to check absolutely everything. But if you want to be 99.99999999999% sure that something's true, you actually have to check a lot less, right? Because that last kind of like 0.0001% is a lot. It's a lot of extra work to get that tiny bit of certainty. Because like as you get more and more certain, the work you need to do gets more and more. So basically what we're doing with how zero knowledge proof works is that we trade all certainty, and we say that like, okay, we don't want to be 100% sure. We want to be 99.999 very, 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 very sure, but not 100% sure. So, and that means that we're able to hide some of the data. And it actually means we're able to hide a lot of the data. So, yeah.
I thought in this diagram we should have like the proof.
So
the prover will produce the proof, right?
Yeah. So the proof.
The verifier will see the proof.
Yeah. So this is the proof, right? The whole thing is the proof. Like this is what this is a representation of the proof. So the proof gets sent, and then the verifier kind of remembers the Merkle root. They know the checks that are being performed, and then they store the nullifier to make sure that there can't be any more double spends. So this is the first kind of like use case that we're going to talk about. Check the time. Okay, cool. So yeah. So is there any questions up until now? Yeah, feel free to interrupt with questions and stuff as we're going.
So this is the verifier view or is prover view? Yeah, view slide is the prover view.
I think it's verifier.
Yeah, that's what I'm saying.
Yeah, so this is the
What's the type of?
yeah, this is the okay. This is the prover view.
Yeah. And this is?
And the next verifier view.
Yeah, this was type of this.
Yeah, that's, I'm sorry. Yeah, so this is the verifier. Yeah. This is verifier because we're hiding stuff. This is like, yeah, there's less information here. Yeah. Cool. Any other questions? So like all the first part of the presentation, that's like the hardest part. So like the next, I think that's like the peak of the hardness of the whole presentation. So like the rest of the time, we're going to be talking about like use cases of this. So congratulations, you can all relax now a little bit. We did the hard stuff, and I probably should have warned you before we did the hard stuff that we were going to do some hard stuff. I will do that next time. But like like we got over the hardest part. If like some of it didn't make sense, the best way to let's abstract away, and then later we can go back and worry about it. So let's just get a high level view of what what we talked about actually does. So basically, it's like a proof of membership. Yeah, you're just proving that you're part of a set, and you're proving you're part of a set in a way that like you can't repeat. And like that's it. It's just like a private way to prove, oh, I'm part of this group, and I'm not able to make another proof of that. So this can be used for a whole bunch of different things, not just for private transactions like with Zcash. And like, let's talk about some of those other things. So one of those other like like in order to like enable some of those other things, we made this tool called Semaphore. And basically, what Semaphore is that it's a way to.
Sorry.
Okay, cool.
So it's small.
Yeah. Oh yeah, that's nice.
Sorry.
It's all good.
Okay.
Okay.
Yeah.
Thank you. Can you hear me? Is that good? Yep. Okay. Ah, that's nice. Okay. So yeah, so Semaphore is a way to prove. It's just a generic proof of membership. Yeah, it's just a generic proof of membership. It's like, oh, I'm part of a group, and that's it. And like, so let's see how it works. Okay. Yeah, so it's just a generalization of Zcash. It's what we talked about before. It allows us to reuse. Like in the previous example, we had a nullifier that meant it was only a one-time use. But we have this extra kind of step here that allows us to reuse the nullifier. And so what can we do with it? We can build some like private voting applications where we could build like a ZK DAO. We could build some anonymous social media. There's a whole bunch of different things that you can use this to build, because like basically it's a way to have like private proof of membership. It's a way to prove, oh, I'm part of a set, but I'm not going to show exactly who I am. So let's look at some applications of this. Yeah, so let's look at some. Do I go straight to the? Okay, so let me warn you again. There's a little bit of hard stuff coming, but it's only a little bit. And we're going to add something else to our circuit that we talked about before, and we're going to add this new. We're going to use a new primitive, and our primitive is basically Shamir secret shares. And the way that Shamir secret shares work is it's like revealing a tiny piece of information that's meaningless. But if you reveal a lot of information, then all of your secrets are revealed. So it's like this sort of threshold thing that if you reveal one share, then nobody really knows what you revealed. But if you reveal more than one share, then everyone learns your private key. So it's another way to do rate limiting, and we call this like RLN, which stands for rate limit nullifier. So it's another type of nullifier. Instead of being like just black and white on and off, it's like stop or don't stop. There's a limit. There's like, oh, you can do 1 per second or 1 per minute, and this becomes interesting when we're talking about like doing applications like yeah, okay, so let me just show. Okay, that's good. Yeah, I want to talk about this. So let's talk about how Shamir secret shares work. So basically the way that Shamir secret shares work is that like we have a line, right? And on our line, yeah, we have this line, and on our line we have like our private key here. And every time we make a Shamir secret share, we reveal 1 point on this line. And okay, so this is the hard part. This is the hard part that will take you back to like high school when you did like what is the
System of linear equations.
Linear equations? Yeah.
System of linear equations.
Yeah. So this will remind you of that when you were doing like that kind of like you had linear equations, you were drawing lines, and like one of the things that like you might remember is that like if you had a line with 1 point on it, it's just a dot. You don't know anything about that line. But if you had a line with 2 points on it, then you know everything about that line. You know every single point that that line goes through. And basically what we do is we leverage this and we say, oh, well, if we have a line with 2 points on it, if we know 2 points on the line, then we know every point on the line. So we say, right, let's force our user to do a couple of things. Let's tell our user, okay, you can make a line, but 1 point on that line has to be your private key, and it has to be at this position. And then every time you make a proof, you have to reveal a random point on that line. And with those 2 things, we're able to force our user to make only a certain number of only one. Oops, I wasn't planning to do that. Yeah, with just that, we're able to force our user to make only one transaction or only one action every epoch. Okay, so this is our private key. Our user reveals a random point. If they reveal 2 points, then game over. We have enough information so that we're able to calculate their private key. So that's how ORLN works. So let's talk about like, okay, so but what does our circuit look like? So let's go to the next slide. Oops, too many slides. Oh no. Ah, it's a little bit lag. Okay. 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 Cool. Okay. Yeah. Cool. Yeah. Ah, nice. Okay. Okay, cool. So, maybe I can just do next slide. Yeah. Okay. Yeah. This is right. Yeah. So, okay. So this is the nullifier. So this is like what ORLN does. So basically, ORLN is like, okay, we have a Merkle root. We have and we want to do the same thing we did before, right? So we have all the stuff that we had before. We have our proof of membership. We have our Merkle root tree. We have our proof of membership. We have our private key. We have our message. We have all of these things. Like all of this is the same as before, and then we just add this like Shamir secret share thing. So basically, we calculate our line. This is us calculating our line. The private key is at the point 0, and we reveal a single point on the line. And if a user makes more than, yeah, that's good. So is it possible to cycle between those two, to just go back one and forward one, back one and forward one? I think that helps to illustrate what's happening here. So the prover sees everything, but the verifier sees like much less information, because we end up hiding, oh, this one is supposed to cover this A. Yeah, but anyway, so basically, yeah, okay, that's good. Yeah, can we go to the next slide? Yeah, so, oh, the one before. Yes. So this is our prover's view, and like the prover just sees much less information. Cool. Can we go to the next slide? Right. Okay. So let's talk about. So those are our 2 primitives. Okay. The hard part is over. Those are our 2 primitives, and now we don't have any more hard parts. The rest of the time we're going to talk about like applications of these things. So like we have 2 primitives. Our first primitive is like our proof of membership, and our second primitive is our proof of membership plus this like rule of like 1 message per second. So we have one nullifier that like doesn't have consequences, the nullifier, and we have another that does have consequences. If you break the ORLN rule, then you lose your private key and you're not able to participate in the system anymore. Cool. So Skitter is a private social media application that's built using Semaphore and ORLN. So can we get the next slide? Yeah, so here's a link. You can go and visit it. So like, how does it work? Well, Semaphore lets you prove that you're a part of a group, and when you prove you're part of a group, you just make a ZKP. So instead of having posts coming from people, you have posts coming from groups. So you have this group that's like, I think they have a couple of groups to do with like number of Twitter followers. Like if you have like 500 followers on Twitter or 7,000 followers on Twitter, you can join different groups. And like the discussions and the things that these different groups say are like just different. And like, this is just like the first set of groups, but I think with time there are more groups, like maybe we could have like a group for like Ethereum communities in different parts of the world. That might be fun, where people can post anonymously. So you prove that, oh, I'm part of the group, but you don't prove which member you are. Yeah, so they post from the groups rather than their IDs. So like the users' posts are not really attributable to them, but rather it's attributable to the group. So this gives people like some like more freedom to like express themselves without, and it also leads to more like community thinking around like the groups that you're part of and like the way that you want that group to be seen in the world. Cool. So could we get the next slide? Yeah. So here's an example of what it looks like. So this is there's like a couple of basic groups here. The first is one with like 500 followers on Twitter, and like they recently added a feature about dark mode, and this person is saying that they really like the dark mode. And then this is another member of the same group who's replying and saying, oh, sorry, could we go back one slide? They're replying and saying that, oh, well, the dark mode is not really working for me. Is there some, yeah, do other people have a similar issue? Cool, so like both of these are, this is like a private group, and you can have like discourse between the different groups. The groups can talk to each other, and like there's user accounts as well, so users can talk to groups. So that, can I get the next slide? Yeah, this one. So let's talk about like the anonymity set. Like, how big are these groups? This is an important question when you're thinking about private social media or privacy in general. That like always you're proving you're part of a group, but you need to how big that's. Could we go back one slide? Yeah, this one. Yeah, so like the anonymity set size is pretty small. Right now the gold group has like 6 members. I think gold group is like 7,000 followers. Silver is 2,000 plus 5. Yeah, so the anonymity set is pretty small, but like it's like this it's this proof of concept of like a world that is possible, where you have like these bigger applications with bigger anonymity sets and like private discourse and communication. Cool. Can I get the next slide? Yeah. And this is my account. This is a user account I posted when I joined. So you can post from a user, or you can post from an anonymous group. Could I get the next slide? Cool. They also have direct messages, and the way that direct messages work is that they use ORLN. And basically the rule is that like you can send like 1 message per second. If you send more than that messages per second, you break the ORLN rule, and your private key will be revealed. So can I get the next slide? Yeah. So this is what it looks like. This is a chat that I had with like one of the people in the 7,000 Twitter follower group. Messaged me, and like the interesting thing here is that like I don't know which member of that group messaged me. I just know that it's one member of the group, and I'm having like this like DMs with that person, but I just know it's one part of the group. I don't know exactly who it is. And I just basically asked them how many Twitter followers they had, and they just didn't reply to me. I guess they were just too busy. Cool. But I'll let you know if I get a reply. Yeah. So yeah. So yeah, can I get the next slide? Yeah. So then there's a couple of like helpers who are interested in building some ZK application. So like one of them is the Semaphore repo that I shared earlier. I think the slides are public already, so like you can check the links in the slides. But there's a Semaphore repo that might be interesting to build some like private application on top of. There's also this ZK starter app. If I can get the next slide, can I? Thank you. Yeah, so it's a React web app. It's like proof verification. I don't know. Just go back one, and like, yeah, and it has like, I think it's a basic. This is another application that just basically compresses EDDSA signatures together. So this would be like the building blocks of a ZK rollup, for example. You could take this application and build on top of it to make a ZK rollup. Yeah. Okay. Can I get the next slide? Yeah, so here's some ideas for like hackathons. Build something with Semaphore, or like play around with anon groups. There's this other website called Hey Anon, which is which instead of have like, so the problem with like the Semaphore group is the anonymity set is quite small, because it's just like it's a very small group because people need to sign up to join. But like, what if we replace the kind of like signature scheme with ECDSA, the signature scheme used on Ethereum, then we're able to make much bigger groups that don't have a sign up. And that's what Hey and On does. They use this ECDSA signature circuit, verification circuit. So they use like Ethereum's signature scheme instead of like something that's NERC friendly. So it's a little bit more expensive in terms of prover, but it's still pretty interesting. Okay, cool. Can I get the next slide? Yeah. Okay. And this is we have a website and a Discord if people want to join and ask questions or explore our website and our project. Be very happy to have you. So that's the end of the first presentation. Do people have some questions?
We expand more use cases like sharing images, videos, or something else.
Yes. Yeah, you can absolutely. So let me just. Sorry. So the question is, can we add more use cases like sharing videos and audio and things like that? And the answer is, so you mean to something like using Semaphore, you want to have like a group that will privately share videos. Yeah, we can absolutely do that. Yeah, that should be relatively easy. If I can go back a couple of slides to just one of the ORLN ones, or to the one about Skitter, where like someone was posting from an anonymous group, the 500 Twitter followers talking about dark mode one. Yeah, so basically, like the information you're using to your proofs can be anything. It can be you can make a proof that a video came from a group, or you can make a proof that a text message came from a group. The way that we kind of connect the message to the actual proof is we just hash the message, and then we pass the result of the hash into the proof. So the message or the post that you're making can be anything. Yeah. Cool. Any other questions?
Mọi người ơi, trên bàn cũng có tờ giấy, mọi người có thể write down question on the paper if you want to give us, and then we can support you guys with the question. Mọi người có thể viết ra giấy ha. Thì nếu mà mọi người có câu hỏi thì mình cũng có thể được và đưa lại cho anh Barry Whitehat để trả lời. Còn mọi người cứ feel free để đưa ra câu hỏi.
Sorry, yeah.
About the nullifier in Zcash. For key pair, is there only one nullifier?
In Zcash?
Yes.
Yeah, so the scheme that I described here is a bit simpler than the Zcash scheme. So I think that the Zcash scheme, the old version of Zcash scheme, it did have just one nullifier, and it was, I think it was a hash based on SHA-256.
So then for a key pair, I can only use it once.
Ah, right. So yeah, that's true. So like that's like you're getting at it. Like there's two issues here, it seems. The first issue is that like I can only use a key pair once. The second issue is I can front run someone's transaction. If I see a transaction that has a nullifier, I can create another leaf that has that same nullifier, insert it into the tree.
A different key pair with the same nullifier.
Yeah, but because like the scheme that I described was very simple, and it would allow this attack because like the nullifier would be the same, but like basically they make so anyway, to avoid that attack, they basically make the nullifier be determined from the private key. But the Zcash, I think the way that it works is they generate a new nullifier for each coin, but they keep the same private key. So like each coin has a different nullifier, but the nullifier is derived from the private key. So when you make the transaction, the nullifier is defined.
So actually, the way that the nullifier is disconnected from the
sorry, hold on, just with the mic. Yeah.
Okay, yes, thanks. So actually, you see, like the nullifier is hash once, and then hidden in the Merkle tree. And then as long as you don't review that leaf, nobody can get the Merkle proof and generate another zero knowledge proof, in which also has the signature for the transaction that you are signing. So you cannot modify the transaction or use the nullifier to authorize another transaction.
Right.
So yeah, so you know, I don't think it is actually related to the connection between the nullifier and the private key. You can have the
right. So okay, so let me repeat just to make sure I understand what you're saying. So basically, what you're saying is that like Zcash's private key, the nullifier is determined from the private key, but in the scheme that I'm talking about, it's not. It's completely up to the user to decide what their nullifier is, and like that scheme is broken because if a user is able to define their private key, then or their nullifier, they're able to just set the nullifier to be another user's nullifier, and that could be an issue. So we can't do that, basically. Sorry, that.
So what I'm saying is that even with the nullifier, you still don't have the Merkle proof. In order to generate the zero knowledge proof, that is necessary to let people validate the transactions.
Right. So okay, let me draw on the whiteboard. So like, I'm sorry that like we got a little bit off topic, but I'm going to come back to your question in a little bit. So right. So basically, here's the attack. Like we have, this is our tree one. Okay, and then this is my leaf here, and this has like a private key of 21 and nullifier of 32. Okay, so like the first thing that happens is I make my ZKP, and I reveal my nullifier 32, and I broadcast this to the network, right? And the network is sort of mining my transaction. Then a malicious person comes along and they see this and they see, oh, the nullifier is 32. So what they do is they make two transactions. The first transaction is that they add another leaf to the tree that is 22. The private key is 22, but the nullifier is 32. They use the same nullifier as me. And like, because I've revealed my nullifier to them, they're able to like insert this leaf into the tree, and then they make a ZKP. And that reveals the same nullifier 32. That reveals the same nullifier 32. And like, when you reveal the same nullifier, only one of these proofs will be accepted, right? There's this race condition. Like basically the attack is a griefing attack. I don't steal anyone's money. I just cause someone to lose their money. So like in this case, like if this leaf was like 100 or 1,000, this user could make one that's just like 1. Yeah, this is like 1,000 coins. This is 1 coin, and like basically they're able to like for the cost of 1 coin, they're able to delete 1,000 other coins. So like. Sorry, go ahead.
Yeah, okay. I see your point. So it's basically a denial of service attack.
Yeah, exactly. So you're able to like delete people's money. So like that is one of the things we have to be careful about when we generate the nullifier. So back to your question. Sorry. Does this make sense so far?
Yes, it makes sense.
Yeah. So your question was like, how does the nullifier scheme work in Zcash? Do you have to generate a new nullifier every time? The answer is no, you don't. And the reason for this is that like the nullifier in our simple scheme was defined as just like whatever the user wants it to be. But in reality, the nullifier will be defined as like the hash of this or something. The nullifier will be defined as like something that's deterministic, so that like an attacker isn't able to set whatever nullifier they want. So because it's something deterministic based upon the private key doesn't change all the time. The private key is constant, and the nullifier just changes depending on like which leaf it is. Like the simplest approach is that we can have the nullifier be the hash of the nullifier, 32, and the index of the position of the leaf in the tree. That this is position 0, this is position 1, so it'll be the hash of this and 1, and that kind of breaks this attack, but it still means that, yeah, that breaks this attack, and it allows us to have nullifiers that are like different all of the time, but you're not able to double spend because the leaf never moves in the tree, right? So with this, you can have the same nullifier everywhere, but it'll look different each time, right? So let me give a more concrete example. Okay. Okay, let me give a more concrete example. So this is our tree, and this is just the nullifier. So this is nullifier. So this is my leaf. This is my first leaf, and my nullifier is 32. And this is my second leaf, and my nullifier is also 32, and my private key is 1. Right? So we just need to change our nullifier scheme. So we just add something else to the nullifier, and the thing we add is the position in the tree. So this can be 0. This is 1. This is 2. This is 3. So just position from like left to right. And then basically when we calculate our nullifier, the nullifier of this is going to be the hash of 32 and 1 and 0, and the nullifier of this one is going to be the hash of 32 and 3. Right. So that's like just a better nullifier. So you can see that we can use the same leaf. You can see that we can use the same private key. It's exactly the same. So the user only has to back up one thing, remember one thing. And the nullifier is always going to be different because it's the hash of different things. So yeah, I think that's it's a slightly more sophisticated scheme that solves the two problems that we talked about. Yeah, no worries. Cool. Any other questions? Also, you can put, if you're watching online, you can put questions in the chat.
Let me check if there's any question on the live stream.
Okay. Okay. So Quinn, I was thinking that like now we might take a little break because it's like a natural break between like the first part and the second part. I don't want to talk for 2 hours and just everyone fall asleep. Okay. Okay. Yeah, we good to start? Okay. Okay, so the second part is a little bit less planned. I wanted to talk about some layer 2 things and like how different stuff works. I don't know if people have a preference about what to explore. Like basically I was thinking to talk about like bridge security and like optimizations on L2 and how to do things like cheaply or more efficiently. That was my plan. Do people have like some interesting like layer 2 stuff they want to talk about? Or some questions about layer 2 stuff? Yes.
So your name is Whitehat. So
yeah.
You the Whitehat person.
What?
You are the Whitehat.
Oh no, that's a little bit. Let's discuss that later. Yeah.
Anyways, talking about Whitehat, I'm
interested in the bridge security.
Oh, the bridge security. No. I was just thinking to discuss about bridge security, about how to make secure bridges. Yeah. Okay. Okay, cool. So, all right, let's get started with like, let's talk about like a basic introduction to like rollups, and let's talk about where's the best place to start. Well, okay, let's talk about a little bit about like the history of like rollups and like what was there before, and like what we ideally want to do. So like the problem is that like on layer 1, we have like a really limited amount of transactions per second, because we want everyone to be able to verify layer 1, because if people aren't able to verify it, then they're not really able to trust it. So like layer 1, we purposely keep the number of transactions per second really, really low, because we want everyone to be able to verify it. But like we also want to be able to build things that scale more on top of layer 1. And one of the ideas to do this is to say that like, okay, so let's make, there's 2 big problems when you have like a list of transactions, or when you have like a block. Okay, so let's talk about per block. So let's take an Ethereum block, and let's see like, okay, what's actually inside this block. So the block is just composed of transactions, and each transaction will do like different things. Like this might be Uniswap. This might be I don't know what else, ENS, and this might be ENS as well. Okay, so these are different transactions that are going to different applications to do different things. So like the way that Ethereum, the way that these transactions are designed is that there's a whole bunch of fields inside these transactions. There's the user signature. Is this big enough? Can people see? Or is that too small for people at the back? Bigger is better. Okay. Right. So what's inside a transaction? So we have a transaction. What's inside it? Well, we have our signature. We have our to, from, amount, nonce, gas price, gas amount, and various other things. I think that's mostly it. So like the signature is just about consent. The to is like the receipt. Oh, there's data. Yeah, data is an important one to remember. The data talks about like what the transaction you're doing does. And the to is like the address and the amount and all this other stuff. So like that's what a transaction is. So like there's a couple of like this is a L1 block, and like L1 blocks are purposefully like really small because we want everyone to be able to verify them. So like how can we get more transactions into a block? Like the first way seems to be to do things about like right. So the first way seems to be let's make the verification easier, right? That like in an Ethereum block, all of the users need to verify all the transactions. But like if we make it easier to verify, then people won't need to make they won't need to do as much work to verify the block, so we can include more transactions in the block. So there's two big approaches to this. One is to use a fraud proof, which is an optimistic rollup, and one is to use a ZK proof, which is a ZK rollup. So like briefly, how does an optimistic rollup work? Okay, so let's go through an optimistic rollup. Optimistic rollup. Okay, so let's talk about an optimistic rollup. So basically, an optimistic rollup has two things. It's like the commitment to the there's a commitment and a fraud proof. So basically, we have this like block creator here. This person is making blocks, and like every time they make a block, they make the commitment. Yeah. So the commitment is basically like this is the result after the new block. The other thing that they make is they publish is a call data. And this is like, you can think of this as like a diff. So we talked about here about the Ethereum transaction format. This is pretty big, but the diff is like a compressed version of that. Like the idea of the diff is that like we want to have the minimal information so that someone can reconstruct the state. So let me talk about like, before we talk about this, let's talk about like the state transition, right? So the state transition is we start in state 1. We start in state 1, and then our block producer here produces a block. And this block is a state transition. So they publish the diff, and we end up with a new state. Okay? And like the reason why they publish the diff is that we want everyone to be able to calculate the new state, state 2, just using the diff and the previous state. And like the reason we do this is we just, and then we end up having like this chain of state updates that publishes just the difference. So why do we care so much about people knowing all of these different states? Like and the reason that we care so much is because we want everyone to be able to execute a fraud proof in case that this state is not correct. Now, like this person is basically just updating the state of our system, and like until now we haven't really talked about like what constrains them or what rules do they need to follow. And basically what we do is we make something called a fraud proof. And our fraud proof will basically say that when you do a state transition, you're only allowed to do the following things. You're only allowed to like, okay, so let's talk about a simple example of just transfers. So like our fraud proof will basically say that like, so you for each transaction, you have to have a signature. So each transaction has one signature. It has two like the from amount. Right. Okay. So hold on. Let me rethink this a little bit. So maybe we shouldn't talk about the simple one. Maybe we should just go for the full EVM. Right. So like this is kind of like what Optimism and Arbitrum do, where their fraud proof is basically the all of the rules of the EVM. So like the idea here is if someone makes an invalid state transition, someone is able to produce a fraud proof that says this is not the correct new state. And like basically they're able to say this state transition, they're able to revert it if someone makes an invalid state transition. So like the idea here is you have a fraud proof that like anyone's able to publish and points out that like this is incorrect and here's why. They give a proof that it's not correct. And that's roughly how an optimistic rollup works. And the reason that's how an optimistic rollup works. Are there any questions so far? You have the mic? The mic? Yeah, I can just repeat your question.
So the process of producing the diff is harder and more computational intensive compared to the fraud.
So Not really. Like the fraud proof and the diff. Oh, so sorry. Let me repeat the question. So the process of creating the diff is more computationally expensive than the fraud proof, and not really. Both of them are very cheap. Making the fraud proof and the diff is just like the diff is just like the like to from amount data. Like that's basically all that you need for an Ethereum block to calculate the new state. Because like once you have this, you're able to like execute the transaction locally, and you end up with the state after the transaction has been executed. Yeah, so that's the so like calculating the diff is pretty easy. It's just like a list of what you changed, right? So like the way that you can think about this is that like we started in state 1, our block creator publishes a list of what they've changed, and then we end up in state 2. Then if the list of what's changed is not correct, someone can make a proof that points out, hey, this one is not correct. And if they do that, a proof to go from state 2 back to state 1. Right? So that's basically the idea of optimistic rollup, that we have this like two-way path that we can go forward where we make like new blocks, new state transitions. We can also go backwards where someone can produce a fraud proof and say, hey, this is not right. So like the kind of equilibrium that we settle into is that like if people are making like valid blocks, we keep going forward and you can't go back. If someone makes a valid block, we can go back and we just undo what's been done. So like, sorry, does that make sense?
The diff is not like professional for one different transaction.
Yeah, the diff, that's what the diff is. The diff is like a compression of like a bunch of Ethereum transactions, but it's not compressed using like you could compress it using some compression algorithm, but normally it's just like the diff is like, actually that's a really interesting topic, diff compression, that we're going to talk about later, about like how can we reduce the size of the diff as much as possible, because like that gets into another thing I'm also going to get to later, because like like one of the key takeaways from this workshop, I think, is that like the only thing we need to optimize for is the diff compression. That's the key problem for scaling layer 2 or for building layer 2 applications that scale. It's
I was thinking if the diff is like easy, everyone can do it, then how can we scale include all of transactions and increase?
right. We like I don't quite understand. I mean, I think the diff is easy. I mean, it's like, and it's good that it is like with an optimistic rollup, anyone can be the block producer. Anyone is able to come forward and make like anyone is able to come forward and make blocks that process the yeah. Does that make sense? Okay. Yeah. This part is like yeah. I think that in reality we very, very rarely go back. We basically never go back, because in a case where we go back, someone ends up losing like 32 ETH or something. Like because of that, the incentives to make invalid blocks are really, really low. We only go forward. We almost never go back. Like going back is just very expensive. It just costs a lot.
Yeah, so we can only set the proof like in the previous step, right?
Oh, so yeah, but like, so I don't quite understand your question. Like when we send the fraud proof, I don't quite understand.
Yeah, for example, trading.
Yeah.
We see that there is a fraud in the state 1.
Yeah.
And we set a fraud proof for state 1.
Yeah. So then we will go back. Okay, so like if that happens, so we have S2, state 3. So like your question is basically like state 4. So if let's say we're in state 4 and we find out that there's a fraud proof, there's a fraud here. So, and you're asking like what will happen? So what will happen is we'll roll back all of these. We'll go all the way back to state 1. And like this one, each one of these will be slashed. So there's 32 slash here, 32 here, 32 here. So like it'll end up just having this like huge slashing event where like a whole bunch of different people lose their security deposits, and everyone just comes back to the very start. Yeah. So like that's one of the concerns here, that like when frauds happen, I think that they will be found pretty quickly. But if they don't, it can cause the state to go back pretty far. I think that it can go back. Yeah, it can go back, like it can't go back to 0. There's normally like a limited time period in which you can publish your fraud proof. But like my understanding is that like it'll pretty regularly, the fraud proofs will be, like if there's a fraud, the fraud proof will be published almost immediately, because the reward is so big. When you think about like MEV and things like that, the reward is much smaller than the reward here for creating a valid fraud proof. Yeah. Yeah, sure, no worries. No. So like this is the basic idea of optimistic rollup, that we have a fraud proof and we have our diff. So let me write fraud proof here. We have our fraud proof as well. So if something isn't right, then we're able to just undo everything we've done and go back to the start. So this is like the basic optimistic rollup, and like basic ZK rollup is very similar. Instead of having a fraud proof, we just have a validity proof. Instead of having a fraud proof, we have a validity proof, and then our validity proof basically, we're not able to roll back, we only go forward. So every time you make a block, you have a proof that the block is correct. Yeah, so we only go forward. You only go forward and you make a block that things are correct. And we also, yeah, we also keep the diff. We have our diff, and it's almost exactly the same. Yep. Okay, so that's basically how optimistic rollups and ZK rollups work. So what's the major so what are the cost savings here? I mean, like why are we doing this? Like the first reason of why we're doing this is that like the first reason of why this is more scalable is that like we're just putting the diff on chain, we're not storing it. So the diff is like the expensive thing now, but we're not storing it, we're just putting it on chain. The other reason why this is cheap is that like either we're executing a ZKP that's super cheap, or we have a fraud proof that's almost never executed. Because if a fraud proof gets executed, it's like 32 ETH will be destroyed. So these are the two kind of big approaches to scaling at the moment. And like both of them depend upon people putting the diff on chain. So I start to think that like one of the other key takeaways that I have when I think about like moving from layer 1 focused development to layer 2 focused development is, one of them is diff compression is super important. The other is that like execution is basically free now, right? Because execution doesn't cost anything anymore, because either you have a fraud proof which never gets executed or almost never gets executed, whenever it gets executed, somebody loses 32 ETH, which means that it's very, very rare. Or you have a validity proof that's super cheap to verify on chain. So like execution is free. The thing that's expensive is like publishing the diff. So what is the cost of publishing the diff? So the diff is basically published as call data. And like call data is very cheap, but it still costs. So let's compare the two. Let's look at the diffs of ZK rollup and optimistic rollup. Okay. So this is that signature. Okay. So let's have a look at optimistic rollup. Optimistic diff. So what is going to be in our diff? So 2. Who are we sending the money to? From? Who is the money coming from? Amount? How much is it? Data. What is the contract call data? What's the, like if I'm calling Uniswap, what is the function signature? What is the function parameters? The key thing that's expensive for optimistic rollup is signature, right? Because the fraud proof needs to check the signatures, optimistic rollup ends up including a whole bunch of signatures. So this ends up being the big cost. Because a signature, an ECDSA signature is like, it's big, especially when you have one per transaction. So that's the optimistic rollup diff. Let me do the ZK diff. So the key thing of the ZK diff is that we just don't have the signature. Because the signature is checked inside the ZKP. The ZKP is like implicit proof that the signature exists. Data. So because of that, ZK rollups can scale a bit more than optimistic rollups because they just have to put a lot less data on chain. That's been one of the like key features of ZK rollups for the last while, or key like selling points that like the transaction cost is just a lot lower. But there is some optimizations that we can do to make optimistic rollups and ZK rollups equivalent. So let's talk about them. So this is the signature when we use ECDSA. This is when we use ECDSA signature scheme. But if we use BLS signature scheme, BLS is just another kind of signature scheme. Well, BLS signatures can be compressed. So basically, if we use BLS signatures, we can just get rid of all of this. The signatures basically goes away, and the call data cost becomes equivalent to ZK rollup. So like we have a project called BLS Wallet. Yeah, that uses BLS signature, replaces ECDSA with BLS signatures, so that like we're able to, so optimistic rollups and ZK rollups can have the same like transactions per second. Cool. Let me check the time. Okay, any questions so far? Okay. Nice. Okay, let's talk about some security stuff. Yeah. So like a lot of the Ethereum community has been worried about the like bridge security of layer 2. And like I think that like bridge security is like an important thing. And I think that before we discuss bridge security for optimistic rollups or ZK rollups, we should first discuss bridge security from one chain to another. So let's talk about that. I'm gonna clean something. Is it okay if I clean this one? Yeah. Okay. Okay, so bridge security. Okay, so let's say we have like two chains. Chain 1 and chain 2. And they like want to talk to each other. So when they're trying to talk to each other, like how can we make one understand the other? Well, like what we talked about already is like, oh, can we have a fraud proof to let them talk to each other? And the answer is basically no, we can't. And like we can't have a fraud proof because chain 1 and chain 2 have their own consensus mechanism. And sometimes those consensus mechanisms change. Like sometimes we have like hard fork, where like one chain will start to change its behavior. Other times we might have some, yeah. And like sometimes we have a hard fork and like when a hard fork happens, it's impossible for like chain 1 would have to, like if chain 2 hard fork, chain 1 would need to also hard fork in order to be able to continue to support it. So we're not able to have a fraud proof and we're not able to have a ZK proof because like these bridges wouldn't really be upgradable. I think that like we could have one that would work for like a short amount of time, but later the connection might be broken if there was a hard fork. The other kind of big issue when you try to have bridges is that like the consensus, like you can have a bunch of different valid consensuses on the other side, and it's impossible to tell which one is actually correct. That like, okay, so let me give you an example of this. Let's say that there's like 51% attack or censorship attack. Like there's been some talk in Ethereum recently about censorship attacks. And basically the defense against a censorship attack is a user activated hard fork. And the way that would happen is that the users on Ethereum would basically say, okay, so let's describe the censorship attack a little bit. So let's say that like we're on Ethereum, we're in proof of stake world. We have like users on, we have like stakers on are having a bit of a disagreement. These stakers are saying that like this is the valid state, or this is the valid state, but like a whole bunch of other stakers are saying, no, this is the valid state. These stakers are saying that this is the valid state. And like, what is the difference between these two states? Well, this one includes transactions to a certain smart contract and this one doesn't. And like, what happens if this side has more of the stake? This is like 60% of the stake. Like the rules of the consensus algorithm basically say that like these people are in charge. They're able to censor whatever transactions they want, and the other group isn't able to really defend itself. Like, but like that's not what Ethereum is though. I mean, like Ethereum is like defined by the Ethereum community, and like if the Ethereum community wanted to say that like this is the actual valid Ethereum, that's their right to choose. Like they're the people who need to make that decision, not like whoever happens to have 60% of the Ethereum stake. So basically what would happen is that like we would have a user activated hard fork where all of the users of Ethereum would say that like this is the new valid Ethereum. This is a new one. And like this is a very important defense mechanism for blockchains. They need to be able to have this mechanism to upgrade so that like if there's an attack, if there's a censorship attack, we're able to like coordinate a recovery, or a recovery can be coordinated by the community, by the users of the system. And they can basically say that like these people just lose their money and everyone else just keeps going. So like this is what we think about when this is like one thing you need to think about when you're thinking about trying to build a bridge from one chain to another. Because like when we're trying to build a bridge, like how can your bridge capture this nuance of like this is the new valid state or this is the new valid state? That's what makes bridges really difficult, because you can't have ZKPs and you can't have fraud proofs. So what people end up doing is they come up with like multi-sig bridges and things like that. And multi-sig bridges are like inherently centralized. And because they're inherently centralized, they're easy to hack, right? They end up getting hacked a lot. There's been a lot of news about like different bridges getting hacked and like a lot of money getting stolen from them. So this problem is just really hard, because it's trying to connect together like this system that's not just like the rules of Ethereum. It's like the rules of Ethereum plus like all of the Ethereum community and its beliefs and philosophy. Like that's really hard to encapsulate. Yeah, that's really hard to encapsulate. So, yeah, so it's really hard. So people end up making multi-sig bridges, which end up getting hacked a lot. And that makes people think that like all bridges, even layer 2 bridges, are inherently vulnerable to these kind of attacks. But that's not true. So let's talk about like layer 2 bridges. So let's talk about layer 2 bridge. So hold on, is there any questions so far? Okay. So let's talk about layer 2 bridge. So a layer 2 bridge is very different, because it's not like one chain talking to another. It's like inside Ethereum, we have like a smart contract that has state, but it also has like a fraud proof, or ZKP, that proves that like the state is correct. Because both of these things are true, your withdrawal mechanism can just be a proof about the state. Can just be a proof that like in state this, I took 100 USD and I sent it to the withdrawal. Yeah. I took 100 USD and I sent it to the withdrawal contract. And then we have a separate contract that just lets you withdraw that money. So this is fine, because anyone is able to make this proof that like this transaction this transaction is valid. So everyone is able to, everyone knows the state. Everyone knows the state, so everyone is able to make the state proof, and anyone is able to withdraw their money. So this is what makes like layer 2s decentralized. This is what makes layer 2s inherit their security from Ethereum. But the key thing to remember is that in order for everyone to know this state, we need to make sure that this diff is published on chain. That's the reason why we publish the diff and the call data, so that we're able to build these trustless bridges, so that users are able to withdraw whenever they want. Yeah. Yeah. Okay. So let me draw that a bit more clear here. So this is like L1. This is L2. L1 and L2. So like this is actually part of L1 as well. This is a separate contract. So this is part of L1 too. This is just like another contract on L1. And like, yeah, that's how the withdrawal works. The deposit happens in a similar way. That like instead of the proof going, instead of the state coming here, you have like a message bridge that like passes the messages from L1 to L2. So this is why we can build like trustless layer 2 bridges. And this is like the whole point of like publishing the cold data. The point of publishing the cold data is that like anyone is able to withdraw unilaterally whenever they want. So if there's like a censorship attack on a layer 2, people are able to, that's a good thing to talk about. So, but wait, questions? Okay, great. So, okay, let's recap. So far, we've talked about what layer 2s are, how they work, what like a cross-chain bridge is, how that works, how to build like a trustless layer 2 bridge. And we also talked a little bit about like consensus layer, like censorship attacks on layer 1. But now, let's talk about a censorship attack on layer 2, and let's consider like the implications of that. Can I delete this one? No. Okay.
Very complex. Are you implying that L1 to L2 bridges are more secure and more censorship resistant compared to cross-chain?
Sure. So the question is, am I implying that L1 to L2 bridges are more secure and censorship resistant than L1 to L1 bridges? Yeah. So
L1 to sidechain.
Yeah. So L1 to sidechain is the same as L1 to L1.
Yeah.
So like at least in my definition, yes, I am. Yeah, that's exactly what I'm saying. Yeah, that like L1 to L2 bridges are inherently more secure because we have a fraud proof and we have data availability guarantees that are all coming from the same place. All of those guarantees are coming layer 1. And because of that, if we have like some censorship attack or something like that, the layer 1 will automatically update to change. Like when that layer 1 is fixed, the layer 2s will inherit that fix. Cool.
So how can we connect between the layer 1 and layer 2, especially the liquidity problem?
The liquidity problem. Right. So like, okay, so sorry, let me repeat your question. So the question is, how can we connect layer 1 to layer 2, especially the liquidity problem? Right, so connecting layer 1 to layer 2 is relatively easy. Like you can just do deposit and withdrawal bridges, like as I defined already. The liquidity problem that you're talking about is that like optimistic rollups have a delay period when you withdraw. And basically the delay period is there in order to give time for someone to submit a fraud proof for like some invalid block. Because of this is a delay period, and the delay period it means that like there's a liquidity problem that I deposit into optimistic rollup and make a transaction, and then I have to wait a couple of days in order to be able to withdraw. That's a liquidity problem, and like there is some ways to solve that. Like we can have bridges that are more complicated that allow people to like upfront give you the money to withdraw and for a slight fee. The other idea is that like you'll just have optimistic rollups that are EVM compatible, so you can do as much stuff inside as you possibly. You can do as most of the stuff you want to do inside, but there is always going to be this delay period for optimistic rollups. And that's another argument for why like ZK rollups are better. But I think that like both are good, and like it's important that we pursue both approaches because it's important we pursue both approaches because like number one, we need diversity in the ecosystem. And number two, I think that the approaches that will be the most secure are hybrid systems where there's a ZK and an optimistic combined. So there's a fraud proof and a ZKP. And like I think that will be the most secure layer 2. It's something that has both, because like it will be like both would need to be broken in order for the system to break. So yeah, I think hybrid systems make a lot of sense. Cool. Okay, layer 2 censorship. Let's talk about this. Okay, so we talked about layer 1 already. We talked about like censorship attacks on layer 1. Let's talk about censorship attacks on layer 2. So we have our layer 2, and we have a set of people who are able to make blocks. And we have some there's some rule for these people to be able to make the blocks. And what they do is they make blocks every once in a while. This is S1, this is S2, state 1, state 2, and this is just what they do. It's just these set of people who are able to do it. So, right. So, okay, so how do we decide who these people are? That's our first question that we need to think about. So like when we're talking about layer 1, the way that we decide who these people are is with proof of stake. But the issue is that proof of stake of layer 1, sorry, let me slow down. So I think that proof of stake on layer 1 makes a lot of sense because we can always have a user activated hard fork in order to be able to continue the system and in order to recover from censorship attacks. But we can't have such a fork on layer 2, right? Because like that would basically mean that like a layer 2 would have to ask layer 1 to have a hard fork in order to fix that layer 2. And that seems like it might be difficult to do. It might be difficult. It's very difficult to get Ethereum to hard fork unless it's like some very serious problem with like the layer 1. It's like Ethereum has historically not hard forked to fix broken contracts. And like I think that they would view like a broken L2 as like just another broken contract. So that's the concern of like having proof of stake as like the way to decide who's in charge of the layer 2. So there is a bunch of other mechanisms that we can use. I'm not going to talk about those today, but what I am going to talk about is like some things that we can do to mitigate the power of these people. So the first thing that we can do to mitigate the power of these people is to have this concept of like forced transactions. So that's basically something that like, it's a mechanism so that on L1, you can submit a transaction that these people have to include. So it's like forced. So you can do that when there's like some kind of censorship attack. You can submit a transaction that they're forced to include. And like the extreme case of this is that like if they don't include that transaction, the whole rollup stops. There's no way for it to continue. And like the more extreme version of this is that like if they don't include a transaction, the rollup stops and like they're not able to make, they just lose their position and someone else can come forward and like continue to make the proofs. This is another reason why we want to publish the call data, because if the call data is published, then if the call data is not published, it's not possible to replace these people because you won't have the state of the system. If you don't have the state of the system, you're not able to like continue to update the system. So that's defense number 1 is forced transactions. So like what are some limitations of this? Like some of the limitations of this is that like you can force transactions and like mostly what people would do, like you can force transactions, but forcing transactions is more expensive than just having transactions included naturally. The reason it's more expensive is because you need to do like a single on-chain transaction in order to force a transaction. And that's hard to do. That's expensive to do. There is some ways that we can optimize it, but like it will always be like slightly more expensive because you will need to do a little bit of extra on-chain work. And yeah, because of that, it'll be a little bit more expensive. So the other problem is that like, so like probably what will happen is that like if a layer 2 is broken, I'll withdraw all of my money. I'll just say, if a layer 2 has a censorship attack where the block producers are refusing to create blocks, I will create a withdrawal transaction that says, I'll create a forced transaction that's a withdrawal. and I'll just say, oh, I want my money. I'm going to go to some other rollup or some optimistic rollup. But this is not good. This is not good because, like, number one, it's very expensive. I need to withdraw from layer 2 and deposit into another layer 2. I need to do a forced transaction on layer 1, and I have to do at least one layer 1 transaction to move my money from one layer 2 to another. And that's just going to be super expensive. And it's especially going to be super expensive when we get to a point where we have millions of users on a layer 2. Not only will it be super expensive, it'll be just practically impossible for those people to move to another layer 2. So because of that, we really need to be careful about leader election on layer 2, because there's this like natural monopoly effect of like when a layer 2 gets big, the people in charge of making blocks become very powerful. Yeah, so the people in charge of making blocks become very powerful. So this is something that we need to be very careful about. Yeah. Any questions so far? Cool. Okay. Yeah, so we have our forced transactions, which is kind of like this exit feature. We could also have something that's like much cheaper forced transactions. It might be possible to make a forced transaction that doesn't require you to do an L1 transaction in order to move from one layer 2 to another layer 2. So like maybe we would be able to kind of join them together by making some kind of specialist withdrawal mechanism. I'm not sure.
Like layer 2 just for forced transactions on layer 2.
So it's like a layer 2 just for force. Yeah, exactly. Yeah. Okay. Yeah, I think I'm getting to the end of like what I had prepared. Like, is there specific problems that people want to talk about, or is there questions that people have? Yeah.
If we can move to layer 2, so why Ethereum decide to switch from POW to POS?
Okay, so the question is, if we can move to layer 2, why did people switch from proof of work to proof of stake?
Yep.
Right. So there's a couple of reasons. Number one, it provides better user ownership of the network. When we talked about like user activated soft forks, that's a lot easier to do with proof of stake, and it's practically impossible to do with proof of work, because like in that case, the people who are making blocks, like okay, it is possible to do with proof of work. That's true. You can just like revert a whole bunch of transactions, but like the ability to finalize is dependent upon like how much computational power you have or capacity you have. So like because of that, I think that like proof of stake is sort of moving a little bit more towards like more people having access to the ability to be a block producer and validator. But that said, it still is very limiting, because like in order to do proof of stake, you need to have like a whole bunch of E's. You need to have like 32 E's, which might be like prohibitively expensive for the majority of the people in the world. But like we want to get to a point where like everyone is able to stake, but it seems like that might be a barrier to people in the short term. So like basically we moved to proof of work because of the security improvements, and also because of the like ecological impact that like proof of work was using a lot of energy, which we could probably use for more better things. So like that was the other major reason that I thought that we moved to proof of work. Other people have different perspectives on this, and I don't work very closely with proof of stake. I understand it like roughly how it works, but I'm not an expert on that. But that's my take.
Okay, thanks.
Yeah, no worries. Cool. Any other questions? No. Cool.
So I think that like, if no other questions, we should wrap up for the first workshop today.
Yeah.
And,
So one last question.
okay, one last question.
So this is in my opinion, right? So so Ethereum is moving from proof of work to the proof of stake in Ethereum 2.0. And Ethereum 2.0, there will be like about 64 sharks, right?
No, so I think that part has been deprecated. So I think that like Ethereum has moved to the like roll-up centric roadmap. And the idea is that instead of having different shards to do execution, you just have like data availability. Like, so the plan is that like we're gonna do the merge, and after the merge, we're gonna do IP 4844. And basically what IP 4844 does is it just gives you this massive data availability layer. So like you're able to make like megabits of data available per second. And like when we do that, we're going to be able to have rollups that can support millions of users. It's going to be really, really cheap to make these transactions. And like that's the plan. And it drastically simplifies Ethereum's roadmap, because instead of having to have like execution as part of layer one becomes really, really simple. Layer one becomes just like ZKP. Layer one just becomes about data availability or not, and that's all that it really is about at that point. Yeah, so that simplifies a lot the layer one, and it allows for a lot more innovation on layer two to make like more efficient execution engines or different ways of building rollups with better user experience or guarantees or censorship resistance and those kind of things.
So as we know that the layer one blockchain, we are pay for gas fee for the blockchain. How about layer two? Layer two, what is the revenue come from for the layer two?
So like layer twos can have transaction fees as well. Like my hope is that like layer two will be so cheap that like transaction fees will be almost nothing, or that like there will be no need to pay transaction fees there, that you can just do transactions.
Yes.
Like I think we want to get to a place where like users don't have to worry about gas.
Yes, as I know that almost the layer two don't pay the token native for the gas fee, and they can make the revenue from that. And what is the revenue come from for the other source?
Oh, I'm not sure about like I think that like you can take fees from users making transactions, and like that should be enough to pay for the gas cost of the call data and things like that. I think that's already enough to be like yeah, I don't know what the business model is of like getting more revenue. I suppose that like probably what the business model of the layer twos is that like, oh, we want to be these people, so we can do like very mild censorship attacks and just kind of like force users to pay higher fees. I feel like that's the longer term like extractive model of a layer two. But like my hope is that like when that kind of thing does happen, that like we'll have ways for people to migrate to other layer twos if they want to. But yeah, that's definitely an issue or a concern, that like these layer twos might become too sort of like revenue driven, and we need to be careful to make sure that like we can recover from states where that happens.
Okay, sure.
Thank you. Yep.
So I'll just roll back a little bit on what you were saying about the layer one application after we apply the ZK rollup and then like optimistic rollup mechanism, that it only showing the diffs, right, or the blockchain, and then we don't really have to store anything on the blockchain. That's why it will reduce a lot of cost for that layer one. Is that what you're saying?
Yep.
Okay, cool. Thank you.
Yep. Yeah, that's a key recognition that like, number one, you do a lot of that execution, but actually the most expensive thing about most smart contracts is storage. Yeah, but like call data is not stored, but yeah, call data is just kind of put there. You like most rollups, you end up storing one thing. You store like the latest Merkle root. Sometimes you store like withdrawals and deposits, but they're very, very rare. Yeah, no worries. So sorry, your question is like in the future, Ethereum will have a
proof of replication
Proof of replication for cold data. Yeah, I think they will. Yeah, so basically like a proof of replication is just making sure that like the data is available in more than one source, or people have like many copies of the data. I'm not sure exactly what the research plans are there, but like, yeah, there's definitely some thoughts about like having these incentives to make sure that like the data has been replicated. Yeah. And like, there's some fun ZKP things that we can do there, I think. I'm not too up to date on the latest research there, but that does seem interesting.
Okay, I think that like it's time to wrap up the first workshop of Vietnam today. And thank you very much. Thank you very much for do the amazing workshop. And also like me, like not a technical person, but I also can follow the step by step. So I know that like other dev peers also they can follow and learn a lot of things also. Today actually we over time about 30 minutes already, but we should wrap up now because like we also have another like more technical and more deep workshop tomorrow. So please like bring the laptop tomorrow. So we also like can do some challenge and exercise tomorrow with Barry. And also after this workshop, we will like send all of you the recap workshop if you want to rewatch. We also have the video and also have the link for the feedback. So welcome for all of your feedback, and then we also hope that we can do better for the next coming workshop. And by the way, that we still have the cakes and coffee and tea outside. Let's like let's stay for a while and we can mingle around and then do little like talk to each other and like network of it. And then hope to see all of you guys tomorrow. Also, thank you very much.
Looks good.
Thank you so much.
Yeah, of course. Is that good?
Yeah. So like even like I asked for some other dialect, please like follow the content.